Stanford University.
Okay, so this is the first of a series of 2 lectures or mini courses on what is traditionally called physics beyond the standard model. And this is the physics that deals with supersymmetry, extra dimensions, string theory, and finally the multiverse. So we have a long journey ahead of us. Today, I will focus most of my discussion on defining what is the standard model, or as it's called, the standard model of particle physics and cosmology. And after that, I will describe the motivations for going beyond the standard model. And then I'll talk about these various attempts that I enumerated and experimental signatures that these attempts give at the Large Hadron Collider. So we live in very exciting times. As you know, the accelerator in Europe, CERN, the European Center for Nuclear Research, has a collider called the Large Hadron Collider, which has been operating for about 5 years and has just turned on at an increased energy and is going to be testing the theories that we are going to be talking about. So let me begin, first of all, by giving you some overview of the standard model. Standard model is an amazing theory. It is the best theory we have today. It is consistent with all known experiments, and it is also mathematically consistent. So you may naturally ask the question, why then do we bother to extend it? Why don't we just enjoy it and consider it the fundamental theory of physics forever and ever? And the reason for this, I'm going to get to after I tell you some of the great successes of the standard model. And the standard model is abbreviated SM. Okay. So the first success of the standard model is the enormous range of energy over which it is applicable. So the standard model, as far as we know it, applies to the biggest distances in the universe, namely in describing the whole universe itself, down to the smallest distances that have been experimentally probed, which is now about a tiny fraction, like 1,000th or a 10,000th of the size of an atomic nucleus. So the range of the standard model is enormous. It extends from the size of the universe, which is about 10 to the 28 inches, down to 10 to the minus 17 centimeters. So 45 orders of magnitude. So that is completely spectacular. The same theory applies at all these length scales over 45 orders of magnitude. So this is an unprecedented success, and it is astonishing that the theory has been tested in all these length scales. Now, the precision with which it has been tested is different at different length scales. For example, on atomic scales, for atomic physics, it has been tested extremely well with precision of 11 decimals. So so there are predictions of the standard model about, let's say, the energy levels of hydrogen atom, which is known to this incredible precision, 11 decimals. So the theory is good enough to predict the properties of hydrogen atom to this precision. And experiments are good enough to probe the theory at that level, and the two agree. And this is spectacular. This gives you a new definition to what we can mean by truth. This is really precise. So this theory is a part of the Standard Model that I'm sure you've heard about. It's called quantum electrodynamics. It was fully developed in the late 40s and then experimentally confirmed to this level of precision. So this is completely mind-boggling that humans are able to describe things correctly at this level of precision. Now, I should say at other length scales, for example, at length scales of the order of the atomic nucleus, which is much smaller than an atom, the theory has only been tested to a few percent, 10%. At very large distances in cosmology, there are precisions up to 5 decimals. So it hasn't been uniformly tested to this level of precision everywhere, but wherever it has been tested, it agrees with data. And there is a lot to be said about this plot. The reason why we have tested things best sort of on the left side of the plot, where we deal with small systems, is because if the system is small, if it has 1 or 2 particles, it's easy to work out. Once you go to larger and larger length scales, you run into molecules and then long biomolecules, and things get complicated. So you cannot have as precise a test of the Standard Model or any theory that is valid there. As you go to higher and higher distances, things get simple, not because the system gets smaller, but because it is so big that you only care about few of its properties. For example, for the universe, we don't care about what happens to any specific galaxy or any specific star. We just care about the total properties of the universe, the size, the temperature, the pressure, the things that concern the universe as a whole. Okay. Now, the next thing is predictions of the Standard Model. The Standard Model has been verified, has predicted, and by this I really mean not things that didn't exist before it and it itself anticipated, the following particles. It's an amazing list. The charm quark, that was one of the earliest predictions. We'll talk about the charm quark later, so if you don't know what it is, just think of it as a quark that we'll talk about. Top quark, something called the gluon, which we will find out a little later, and the Higgs boson, the famous Higgs boson that was discovered in 2012. And also, and these particles were predicted, their masses were only roughly predicted, but their properties were predicted to levels of percent and turned out to be correct. Then there is the particles that will, W and Z particles that we will talk about today. And these particles, both their masses and their properties had been predicted way before experiments confirmed. So it's pretty staggering that the one and the same theory has made so many predictions that turned out to be correct. And of course, the Higgs boson that happened 3 years ago was the final particle that completed the Standard Model, with the exception of one particle, the so-called graviton, which is responsible for the gravitational force, which we all believe is there, but it is so weakly coupled that it's extremely unlikely that we'll measure it, at least individual gravitons. However, we are looking at an experiment called Advanced LIGO is looking at gravitational waves, which is a large number of gravitons at once. So this is almost the completion of the so-called Standard Model. So this is now, you may now ask what are the general reasons for why we believe it's not a complete theory? not. Okay. The first is that, as we will see in a little while, the standard model has many parameters, many numbers that you have to specify before you can work with it. Many numbers, these are called the parameters of the standard model, and many means approximately 20. So it's not an enormous number, but it's still, it doesn't look like a fundamental theory should have 20 indeterminate parameters. It also has many particles, again about 20. About 20 particles. Same comment. It seems to be too many. Somehow we believe that fundamental theory should have maybe one particle or one entity, maybe a string whose vibrations give rise to all the particles, or something more fundamental. And then a more important problem that has been addressed by many of the theories beyond the standard model is that there are many strange numbers. And what do I mean by strange numbers? Numbers like 10 to the minus 120 that we will talk about, 10 to the minus 30, 10 to the minus 9, and 10 to the minus 5. And all of these numbers are so small that they beg for an explanation. If they were all order 1, we would feel, oh, well, it's about natural. 1 is but something like 10 to the minus 120 seems to beg for a deeper understanding. And finally, what we are experiencing in the last, let's say 37 to be precise, years, is a transition from the questions that have to do with what is the fundamental theory, what's a theory that works at energies where we experiment, to why. So one level of deeper questions. If we look at the standard model, it explains everything. So if we know that the theory, at least at energies that we are experimenting, is the standard model. But now we want to ask, why is the theory the standard model? Why these small numbers? Why are there so many parameters? Could we derive all these things from a more economical entity? And I'll give you an example of a why that the standard model does not address. Why are atoms neutral? This seems like a fundamental question. Electrically neutral, I mean. In other words, in hydrogen, why is the charge of the electron exactly equal in magnitude and opposite in sign to the charge of the proton? If this were not true to a precision of about 20 decimals, it turns out the world would be very different. Gravity would become a subdominant form to electricity. So, atoms that we consider neutral, if they had a tiny amount of charge, they would repel. So gravity wouldn't be able to aggregate them together and form the structures on whose existence we depend on. Stars, planets, etc. So that's very important. And this is answered by what are called grand unified theories. And I will talk about them today. And then another question is, again, in the nature of transitioning from whats to whys, why is gravity so weak? For example, when I raise my arm, I am performing an amazing experiment demonstrating the weakness of gravity. Because when I raise my arm, the electrical forces in the atoms on my shoulder are able to overcome the gravitational attraction of the entire planet Earth. This sounds like a miracle considering how small my shoulder is compared to the size of the Earth. And the only reason why I can do it is because electricity is a far stronger force than gravitation. So this is called the famous hierarchy problem. We'll come back to it several times. And many of the theories I enumerated before are geared to address this question. So the hierarchy problem attempts that I'm sure you've heard about come under the name of technicolor, supersymmetry, large extra dimensions, are some of the approaches, and also, well, string theory at low energies, etc. These are all things that we'll talk about, especially supersymmetry and extra dimensions and strings at low energies. These are attempts to explain why gravity is such a weak force. And finally, why is the universe so large? Universe so large. And what do I mean by so large? Well, when you define the theory, the so-called standard model, typically the theory is defined by, well, the particles that it has and the various forces that it has and the parameters that it has. Now, if you look at all the parameters in the theory, in the so-called the Hamiltonian of the theory, in the parameters that define the theory itself, they are far smaller than the size of the universe. Okay, so the fundamental theory has only sizes of the order of the size of an atom or a nucleus or far smaller than that. The so-called Planck length, which is even smaller than all the other lengths. So how can a theory whose fundamentals have only very short length scales produce an object as big as our universe? And this is called the cosmological constant problem. This is probably the most famous of all problems, cosmological constant. Problem. And the universe, and the reason for the enormity of this range of sizes that I have shown is exactly the enormity of the size of the universe. And the cosmological constant problem is the problem that I was alluding to, involves a number as small as 10 to the minus 120. Okay, this has to do with the size of the universe divided by the size of fundamental parameters like the electron mass or the quark masses, etc. Now, this led to the so-called multiverse, which we will also talk about in multiverse. Okay. So these are some of the topics that we will cover. And now I want to begin with a brief review of the standard model. But before I review the standard model, I want to, or the standard theory, some people like to call it the core theory. There's all kinds of names. Standard model is the most common. So I want to discuss what is a theory. What do theorists mean when they talk about a theory? Okay? I'll start by an example, which is not what I'll work on. The theory of the solar system, or theory of solar system, to have something very concrete. Okay, this was developed by Newton 400 or so years ago. Okay, theory of solar system. So, in what characterizes that theory? Well, the first thing that characterizes, you have to specify the following quantities. First, the masses of all the particles involved. Masses of the sun and the 9 planets. I guess I'm counting Pluto because I'm old-fashioned. So the sun, so that is one mass, m sun. So that's one parameter. That's what I mean by parameter, an example. And then the 9 planets from Mercury all the way to Pluto. Okay? So then there are several masses, m1, m2, 9 numbers. So there is a total of 10 numbers or 10 parameters. Okay? And then I have to specify what's called Newton's constant, G Newton, Newton's constant, which we know from experiment, Newton's constant. Okay? So that's one parameter. So 10 and 1 is 11. So I'm accounting here. Now, we are not yet done. So these are all the parameters in the theory, as we call it, which we call in the Hamiltonian of the theory that defines the theory. There is, to solve, Newton's equations are second-order differential equations. This means that to fully solve them, you have to specify for each particle an initial position and an initial velocity. In other words, you have to freeze time at some point, let's say today, and you have to go out and measure the positions and the velocities of all the planets and the sun at one instant of time. And if you do that, these are 10 objects, and you have to specify you have to specify the position and the velocity for these 10 objects, each one of which is a vector. So it has 3 components for the position, 3 components for the velocity, 6 numbers times 10 objects is 60. Okay, so if you do the accounting now, add it all together, you find 71 numbers. Well, that sounds like a lot, but think about it. Once you specify these 71 numbers, you can predict the whole history of the solar system from 4 billion years ago to eternity, as long as the solar system exists. So this means you can predict the position and the velocity of each and every planet at any time in the past and any time in the future. So infinity of information coming from these numbers. These 60 numbers are called the initial conditions. They are not part of the definition of the theory. They define the initial state of the system. And given the initial state, the equations take over and tell you what will happen in the future and what happened in the past. So you name it, if you include the moon, every solar eclipse that ever happened can be predicted very precisely with these equations. So it's an amazing amount of information. So this is a paradigm for what is meant by a theory. It's a very concrete thing. It has force, in this case gravitational force, and how strong the force is. It has particles, and then that defines the theory, and then it has initial conditions. You have to tell it something like, how did your system start? Once you give it these conditions, you can predict everything. So, and this is the paradigm that modern science through Newton gave us, and that's essentially what we are trying to emulate with all the theories that we're working on these days. Okay, now I want to talk about what is a particle theory. This was a very specific theory, the theory of the solar system. What is a theory in particle physics? It's similar but not identical to what I tell you Newton taught us. Physics. Okay. And the first big surprise of modern physics, that's only a phenomenon of the last 60 years or so, is that a theory in particle physics, a modern theory, is not actually defined to start with from the forces and the particles. There is a more primitive concept that precedes the theory, which is called the concepts of symmetry. Okay, and in a sense, symmetries are more fundamental than the forces themselves and the particles themselves, which is an amazing surprise, because symmetry is something that we are familiar with, is obviously important for the arts. Okay, so for example, a classic symmetry is, oops, I missed something. Okay, I'm missing a slide. I had, let me see this, I have to wait on this. Symmetry, for example, a butterfly, has a symmetry axis around which if you reflect it, it looks the same. And for some reason, this we have learned, here is the picture I wanted, we have learned to think of this as being beautiful. Okay? So another example of a symmetry is a sphere. A sphere, no matter how if you take a sphere, a perfect sphere, without any dots on it or anything, completely, let's say, all white sphere, if you rotate it, it looks the same. Okay? And that encapsulates the basic idea of a symmetry. A definition of symmetry is as follows. An object is said to be symmetrical if you can do things to it and it looks the same before and after you do these things to it. Okay? So that is the definition of a symmetry. The fancy mathematical language is that there is a group of transformations that you can exert on a system that leaves the system invariant. Okay? Symmetry, an object is symmetrical if you can do things to it such that it looks the same afterwards as it did before. That's the idea of a symmetry. This is Hermann Weyl's definition of a symmetry, and the one that is relevant for physics. Turns out symmetries play a big role in mathematics as well as physics. They started in the early 1800s by a young mathematician called Galois, and the symmetries in mathematics are described by what's called group theory. And group theory is a set of rules that is, for example, something is a group if it has operations like rotation. The rotation on a sphere is a member of the rotation group. Okay? And when you say that rotations are a group, it means that if you apply two sequential rotations, then you get a rotation back. Okay? The result of two sequential rotations can be mimicked by a single rotation. Or for every rotation, you can undo any rotation. If you rotate by 30 degrees clockwise, you can rotate by minus 30 counterclockwise and undo it. And there is another rule called the associativity rule, etc. So it's a mathematical structure that has some rules. And group theory has been the foundation of physics for over 60 years now. And symmetries have the following amazing attribute. They define the forces, in particular the so-called gauge forces. I'll use the word gauge later on. They define the forces. And they also define possible particles that the theory can contain. Okay? So a symmetry defines the forces, the so-called gauge forces, and defines possible particles that they. And what do I mean by that? And to explain that, I need now to move to a bit more mathematics and discuss the group, the symmetry group, which I will write down as SO3. And what do I mean by that? I'll explain every symbol. SO3, in brief, is the group of rotations in 3 dimensions. So you take the set of all 3-dimensional rotations, makes a group which is called SO3. 3 stands because space is 3-dimensional. And O is just, it means orthogonal. And orthogonal means that when you rotate an object, you don't change its size. Okay? So that's intuitively obvious, but it's a special property. Not all transformations have this property. If you squeeze an object or you stretch it, that's an example of a transformation which is not orthogonal. But orthogonal means you just rotate it without changing distances, the size of the system. S is some other specialized property. I use it because it's very common. It means volume preserving. It means that if you take a sphere and you rotate it, you don't change its volume. In fact, if you rotate any object, if you take a ruler and you rotate it, you don't change its volume. And so this stands for S. So they are what we call rotations, nothing more. And so this is the group SO3. It's the set of all possible rotations that you can imagine in 3-dimensional space. And it's the most intuitive of groups because we can picture it. You have X, Y, Z, or height, width, and depth, the 3 dimensions of space, and you rotate from one orientation to another. Okay. So this is the most familiar group, and I'll try to develop the standard model, the group of the standard model, by using analogies of this. Now, remember, when you deal with physics, you encounter quantities that are called scalars. And these are quantities that do not transform under rotations. Under rotations. That's an example of a scalar. An example of a scalar is, let's say, the size of a sphere. If you rotate a sphere, its size doesn't change, so that's an example of a scalar. Okay? That's the simplest example. Does not transform under rotation. And then there are quantities that are vectors. Now, the best way to visualize a vector is like, let's say, your finger. Okay, so a vector is something that has a sense of direction and size, how long it is and where it points. So it usually takes 3 numbers to specify it. One is the length of the vector, and the other is the orientation. You need a couple of angles, polar angles, to determine where it's pointing. So a vector is a non-trivial object because if you rotate it, it changes. It points, instead of pointing north, it will point west, etc. So the vectors are, and then there is quantities that are somewhat more involved that we will not use, are called tensors. Tensors are like vectors, but 2 of them at once. So it's something, it's hard to visualize. You can only visualize it as 2 vectors that sort of rotate together. But that's a very rough picture of a tensor. Okay. Now, I will now immediately jump into defining the standard model And I will first write down the symmetry group of the standard model, and then I'll spend some time explaining it. The symmetry group of a standard, first I'll write it down and then explain it. So it's a pretty big group. It's S, the group is SU3 times SU2 times U1, and it's pretty scary, and U1. That's it. First of all, and I'm using observation. These are three of the smallest groups. It's funny that they follow the pattern 1, 2, 3. They are relatively small groups. You can have groups that are much, of course, they can go infinitely big. Nature chooses this group. Now, what is SU3, what is SU2, and what's U1? SU3 is very analogous to SO3. Remember, SO3 was rotations in 3 dimensions. SU3 is exactly the same thing. It's also rotations in 3 dimensions, except the 3 dimensions are now complex. They're not made out of real, the coordinates x, y, and z, or height, width, and depth, are not real numbers, but they are complex numbers. So they have a real and an imaginary part. So it's rotation in a 3-dimensional space that is complex. S, again, S stands for the fact that these rotations preserve volume. Again, it's a technicality that I won't dwell on too much. Same with SU2. SU2 is even simpler. It's rotations in 2 dimensions, like a plane. Okay, so you have a plane, which has, let's say, only width and depth, and you perform rotations. But the plane, the 2 coordinates of the plane are, again, complex. They are not real numbers like x and y, but they are complex. Each one has a real and imaginary part. And again, so this is analogous to SO3. This is analogous to rotations in 2 dimensions. U1 is even simpler. It's like rotations. U1 turns out to be the same, what's called isomorphic in mathematics, with the group O2, which is orthogonal rotations in 2 real dimensions. So it's like, again, just like SU2 was, O2 is a 2-dimensional group. It acts on x and y now are real numbers. Okay? So this is the group of the standard model. Now, to introduce such groups in physics, it took a lot of guts for the following reason. When we talk about, for example, the rotation group, we have an idea about the space the space that we are talking about. It's, let's say, the space in this room, and a vector is like my finger, and it points from here to there. We have intuition, and so we understand exactly what we are doing. When we talk about these groups do not act in our 3-dimensional space. They do not rotate, objects that we are familiar with from one orientation to the other. They act on what's called an internal space. In other words, you have to imagine that there is an abstract space on top of our space, in addition to our 3-dimensional space, on which these symmetries act, these groups act. This leap, I believe the first who introduced what are called internal groups, groups that don't have to do with our familiar 3-dimensional space, but some imaginary space that is Heisenberg. He introduced the concept of isospin in nuclear physics, and he was the first to start thinking that perhaps the proton and the neutron are like related by what turned out to be an SU2 symmetry. You can rotate the proton into a neutron and vice versa without changing the laws of nature, without changing physics. Okay. But it's an amazing abstraction because the space on which these symmetries act are not our familiar space of experience. It's an internal space. Okay. So this is quite amazing, the fact that symmetry has such a role in physics. In the 19th century, people would use symmetries to sort of simplify problems. If you study a spherically symmetric problem, it's convenient to use spherical coordinates because the equations simplify. So symmetry used to be a trick that you can use to simplify problems. You can say, well, the problem is spherically symmetric, so the answer can't possibly depend on the orientation, so that reduces the variables. You can eliminate the directional variables, etc. Here, it's a complete reversal. Symmetry defines the theory. It defines the forces, and it also defines the particles. It greatly constrains the particles that can be present in the theory and defines their possible properties. For example, you may be familiar that when you have scalars, vectors, and tensors, okay? There is nothing in between a scalar and a vector, okay? A scalar has one component. It's just a number, like the radius of a sphere. A vector has three components, like the velocity, the x, y, z, or the position, height, width, and depth. There is no entity with that is 1.5 or 2 with two components in this group SO3. There is nothing in between scalars and vectors, nothing between vectors and tensors. There is no irrational number of, so these are very well defined. So the types of entities you deal with is what's called quantized. It's discrete. You can have a one-dimensional, what's called a one-dimensional representation, which is one number, three-dimensional characterized by three numbers, etc. With tensors, there is five-dimensional, etc. So very few, and they have very well-defined properties on how they change under rotations. Okay, so now now that I said the words SU3, SU2, and U1, I have to tell you much more about them, what they do. SU3 is called the color symmetry and describes strong interactions. Okay? And in a way that we will discuss. So because it's 3, it has the best way to define it is in a three-dimensional space. Normally, we define the three-dimensional space to have x, y, and z components. Those are the typical three. Here, instead of x, y, and z, the three possible directions of space, we call red, green, and blue. And I could have used the right pens to write them down. So instead of, this is like height, width, depth. Instead of calling them height, width, and depth, we'll call them red, green, and blue. And that symmetry is called the colors. It has obviously nothing to do with normal color. It's just to give a somewhat more friendly name to what is otherwise a very abstract entity acting in abstract space. So this group SU3 is extremely important. It describes strong interactions, which is the force that keeps atomic nuclei together, and we'll talk a lot about it. Okay, so that is the that's all I'll say for the moment about the color group. Then there is SU2. SU2 describes weak interactions. Weak interactions are, for example, describe some types of radioactivity. Okay? So they are very important in nature. They are responsible for, a typical thing that happens in nature is that, remember I told you that there are 20 particles? You can say, where are these 20 particles? We just know electrons and whatever is inside the nuclei, which turns out to be just a couple of quarks. All the other particles are very heavy and they decay. And many of them, most of the decays happen through this weak interaction. So heavy guys exist in the theory, but they are no longer today in the universe because they decayed by weak interactions. Weak interactions cause a transmutation. They can change a heavy object to a heavy particle to a light particle and decay. So they can be made, these 20 particles can be made in the laboratory at the Large Hadron Collider, or they can be made, some of them, we'll talk about some of them in the center of the sun, but they don't, they don't live very long. Okay, and then there is U1, which is essentially, it's actually a mixture of the weak and the electromagnetic interactions, but I'll just be thinking of it as electromagnetism. So it's just amazing. Electromagnetism, which is something that we have some intuition about, is associated with this abstract group of two-dimensional rotations in some abstract space. Okay, it's a fascinating thought. Okay, now, how does SU2 work? Well, SU2, as I said, is rotations in 2 dimensions. And here, instead of calling the 3 axes red, green, and blue, well, the 2 axes that we have, we call, it's a confusing name, up and down directions. So red, green, and blue is for color. For SU2, the most commonly used words for the 2 directions in the SU2 space is up and down. Sort of can be traced to Heisenberg. He introduced the terminology up and down for protons and neutrons in his group, which was an SU2. So up and down. Okay? So there are now 5 directions. There is red, green, and blue associated with strong interactions. And there is up and down. Sometimes I should say this is called purple and black. I will actually use this as a color code, black. But up and down is the most common terminology. Few people call them purple and black, just to make them look like colors, just like. And then there is electromagnetism, which, okay? So, okay. Now, what do these things have to do with elementary particles and forces? And that is what I want to explain now. So far, this is just mathematics and terminology, some abstract space, rotations in 3 complex dimensions, rotations in 2 complex dimensions, and rotations in 2 real dimensions, which is U1. Okay. I should say, I'll come back to this. Maybe I should say it now. Remember, I was saying for rotation group that there is only a discrete or quantized representations. They can be 1-dimensional, 3-dimensional, etc. There is no square root of 2-dimensional representation. There is nothing in between. Same thing, of course, is true for SU3 and SU2. So the possible representations, the possible attributes of particles, of entities that transform under SU3 or SU2 are discrete. Just like you can have scalar or vector, or you can have a tensor and nothing in between. Okay? In contrast, electromagnetism, you can have charge 1 times the electron charge, or you can have square root of 2 times the electron charge, or pi times the electron charge, or any number times the electron charge. It's all fair game in U1. So this means that the electric charges of elementary particles are arbitrary. It could have been that the electric charge of the electron is, what it is, and that of the proton is square root of 2. And then the world would be completely different. Hydrogen atoms would repel because they would have a net charge, and everything would be different. The whole universe might not form stars, etc. So nevertheless, this is not the case. As I said before, the charges of the electron and the proton are equal to, experimentally has been tested to 22 decimals, and it's possible to test it to 30 decimals in the not so distant future. So it's a very well-established property. And this is one of the blemishes of the Standard Model, that it cannot, because the electromagnetism comes from this U1 group, you cannot explain what atoms are neutral. Okay, now I will give a little more flesh and blood to these groups. Instead of just telling you how they act, I will write down the particles, some of which you're familiar with, and how they transform under these groups. Okay? Now, a short introduction. So 2 of the particles that all of you are familiar with is the electron, which, let's say, goes around in atoms, in hydrogen atom, and inside the nuclei, okay, so electrons surround an atom, and inside the nuclei are protons and neutrons, typically, okay? So one fundamental particle is the electron. It turns out to be, as far as we know, an elementary particle. The proton, which I will denote by P, is not an elementary particle, is made out of 3 objects that are called quarks. So let me write it, 3 quarks. And the 3 quarks are two what are called up quarks. So this is an up quark, and that's an up quark, and a down quark. This is a down quark. These are names. They are called up and down because of these directions. One turns out to be like one of the 2 components of this, of the directions of this SU2, and the other is like the lower component. Okay, so up quarks and down quarks. So the proton is made out of 2 up quarks and 1 down quark. And if you want to visualize it, this is very common. It's like 3 dots, up, up, down, inside the bag. The bag, you don't have to think that this bag exists, but it sort of gives you an idea that these things move as an entity, a single entity. Okay? And then a neutron, which is called N, is again made out of 3 quarks. And this time it's 1 up and 2 down quarks. And again, you can think of it as 1 up and 2 down quarks bound together. Okay. So these are particles that we are familiar with. The electron, the up quark, and the down quark are inside our bodies, inside the table, inside all matter that what we normally call matter. And as far as we are concerned, the universe could just be made out of these particles and nothing more. As we will discuss, and as is the case, in fact, there is many, many more particles than just the electron up and the down quark. The universe doesn't just care about what we care about, but it has many other particles, sometimes for reasons that we can appreciate, and sometimes for reasons that we don't understand. And so now I will need to, let me keep this. So I defined the up quark and the down quark and the electron that I will need now. And let me erase this. Okay. Now I will write how the quarks, these up quarks, the down quarks, and the electrons behave, or as it's called, transform, under these SU3, SU2, and U1 symmetry. And I will in part write this down to show you how complex the Standard Model looks if you look at it one way. And then when I introduce grand unified theories, this complexity will greatly simplify. You'll see that, oh, it's just one thing. It's in one thing per family, or three things that make up all the world. Things will simplify. But so on purpose, I will write down the so-called how the various elementary particles that we know transform under this symmetry. So the up quark, okay, and the down quark. It turns out the up quark and the down quark, to represent how they transform, it's very convenient to think of the following. Think of the up-down direction being the weak interactions. This SU2 weak is represented by up or down, and the horizontal to be color. So this is horizontal is color, and vertical is weak. So up and down is a doublet, what's called a doublet. In other words, there are two directions to be. The up quark can be is on top, and the down quark at the bottom of this two-dimensional space. And of course, the quarks also have color, and it turns out that the quarks, as we know them experimentally, they have color. They come in three varieties: red, so red, green, the three axes that I defined before, down green, and blue. Okay, so the quarks are a triplet of SU3, so they come in red, green, blue varieties, and a doublet of SU2. They come in up or down, up or down, up or down. And this is what's called this is called the up-down quark doublet. It's usually indicated like this, even though it really represents three different colors of up and down quarks. So it's, if you wish, it's 6 objects, but sideways, the 3 objects are related by symmetry. It's like rotating the x to the y to the z axis. There is no real difference between x, y, and z axis. It's a convention. You can choose the convention any way you want. Similarly here, red, green, and blue are 3 equivalent axes, and you can reshuffle along the horizontal direction and mix the 3 colors of quarks. And similarly, vertical, up and down quark, according to the Standard Model, are not really a different particle. You can switch them around. You can flip them, or you can mix the up quark and the down quark by making a, let's say, 45-degree rotation in this 2-dimensional space. etc. So you can reshuffle things vertically and you can reshuffle things horizontally, and you don't change the physics. That's what it means to have a symmetry. You rotate a sphere, the sphere doesn't change. If you have a theory that has this symmetry, you make a rotation in this three-dimensional space or in that two-dimensional space or in this two-dimensional space, and the theory doesn't change. Everything remains the same. All results of physical experiments. And then it has a hypercharge that I will not specify. It turns out hypercharge is just like a charge. It's like an electric charge. So it doesn't have any multiplicity associated with it. Okay, so that's 6 entities. Well, naively, this doesn't look like simplification. In the beginning, we had up and down quarks. Now, all of a sudden, we multiplied them by 3. Turns out there is, obviously, we know experimentally that there are 3. In fact, there was early evidence that there is 3 colors of quarks from very early on due to I'll get, I may not get into this. There is something that I'm sure you've heard called Fermi statistics, which is sensitive to how many types of a given particle you have. So having 3 cells is very different than having just 1. And okay. Now then there are antiquarks. So it turns out that the antiquarks are also in a 3-dimensional representation, but they are in the complex conjugate. Instead of rotating with some matrices, they rotate with a complex conjugate of some matrices. Rotations are whenever, let's say, a triplet rotates by a matrix, the 3 bar rotates by the complex conjugate of that matrix, and that's the difference. And so we have U bar, these are the antiquarks. Let me see, this is like 2/3. U bar red, this is like the anti-red, the anti-green, the anti. Anti means it transforms like by complex matrix, by the complex conjugate of the matrices that the 3 transform. So this is the antiparticle of the up quarks. When you have particles, so you have antiparticles, and similarly here, you D bar green, D bar blue. So you see how, and these are again 3 bar, 1, and this is, I forget what this is, let's call it a third. Okay? This is actually minus 2/3. But anyway, so there is no SU2. 1 means it's a singlet. There is only one of it. 2 means it's a doublet. So this is a singlet of SU2, and it transforms under SU3. So the up antiquarks transform under strong interactions, but not under these weak interactions, and have, of course, electromagnetic charge. And this completes, these together are called the particles of the particles of the Standard Model that carry strong interactions. And they are generically called hadrons. And in this case, they have the specific name of being quarks. So these are the quarks that we are made out of, if you wish. And inside our bodies, there are these quarks, and there is some component of antiquarks. Okay, so that is the particle content as far as hadrons are concerned. In addition, there are particles that do not carry strong interactions. These particles are called leptons, and they have the following what are called quantum numbers or attributes. There is a doublet, something that carries no strong interactions, but is a doublet under weak interactions. And the lower component of the doublet is the electron, and now comes the first new particle. The upper component is called the electron neutrino. Okay, electron, nu E is the electron neutrino. okay? And then there is the positron, which has these quantum numbers. It carries no strong interactions, no weak interactions, but it has electric charge. And this list completes all the particles that are in the so-called first generation or family. Generation and family are used interchangeably. First generation or first family of particles, okay, in the Standard Model. So with the exception of neutrino, they are all things that we find in matter. The neutrino is very important. It participates in weak interactions. It's important for how the sun works, for how the sun produces energy. So that's the first generation. Now, in addition to the first generation, I should add one more particle. So this is not a member of the generation. I should say, all of these particles are what are called fermions. In other words, they have what's called spin 1/2 to be. Okay? So they are all fermions. The electron is a fermion. The quarks are fermions. Okay. Now, this could be the beginning of a complete theory. And in reality, as we will find out in a moment, it turns out nature repeats this pattern 3 times. In other words, instead of having just one generation and family, which would be enough for us, there is 3 repetitions of this. There is second and third family. And as I said, we don't have a very good reason for why the pattern repeats. It's helpful because if you have 3 generations, it gives you a way to have what's called time reversal invariance violation, which is a fancy thing that has been observed in nature. So 3 generations is only for very esoteric reasons good. Otherwise, we don't understand whether there are 3. We are not done yet. First, there is the Higgs particle, H, which has exactly the same numbers as the electron. So the Higgs particle is -1/2. It's just a doublet. H is equal to Higgs. This is and it is spin 0. That's the big difference. It's the only elementary particle that has no spin. All other elementary particles have either spin 1/2 or spin 1. Okay? This is the Higgs. It has exactly the same properties, characteristics and the upper component is sometimes called H0 and the lower H minus, just like the electron. It has a neutral and charge -1. The first is like the neutrino electrical neutron. The second is like the electron, neutrino electron. Okay? Now, and we are not done yet. In fact, we left out what is arguably the most important component of the Standard Model, which are the gauge fields, the gauge forces. So to introduce them, I will need, I'll actually use the slides because they are much more, there is no pointer. Okay, so let's see. Yeah. Yes. Say that again. No, I don't see it at all. Okay, no, I can do it like this. So here you see I have listed at the top a quark. I chose the up quark. I could have chosen the down. So a quark comes in 3 colors. Now I've represented the colors vertically. Please, I changed convention. So there is a red quark, a green quark, and a blue quark. Okay? So those are the 3 colors of the up quark. Now, let's say that an up quark comes along from left to right, a red one, a red up quark. That's what I'm showing there. And it wants to transition to a green quark, green up quark. It can do that, but only at the expense of emitting a new particle, which is called the gluon. And this is a key, so I will redraw what I said here. So a red up quark comes along, and it wants to convert to a green one. So a red comes here. It wants to convert to green one. And the only way it can do it is if it emits what's called a gluon. And a gluon is a particle that has 2 attributes at the same time. Okay, so let me draw it like this. Gluons are conventionally wiggly lines. The wiggles don't carry any significance other than the fact that the key point to find, so the only way a red can convert into a green is if it emits a gluon, and this gluon has to have very specific color properties. It has to be red and anti-green. So this particle that's emitted is a gluon. Let me write it. That has the attribute that it is red and anti-green. Now, why is that? Turns out this is a very deep thing that because there is 3 conserved quantities. When you have a group SU3, there are 3 characteristics that have to be preserved, and they are called redness, greenness, and blueness. Okay? So these are like, electric charge is conserved, or somewhat analogous to baryon numbers is conserved. Things that are, so redness can never be created out of nothing or disappear. So the only way to annihilate a red thing would be to give that redness to another particle, in this case the gluon. And the only way you can create something green is if some greenness came from somewhere. Okay. So this is a consequence of having this symmetry, this SU3 symmetry. SU3 means there are 3 conservation laws: redness, greenness, and blueness. And so this is how strong interactions react. How much time? Who knows? Okay.
So they're at 8:20 right now.
Okay.
And we go till 9.
Oh, till 9. Oh, okay. Okay, that's fine. Okay. So the only exception to this rule is if you have red, green, and blue at the same time, that counts like it's completely neutral. So you can have you can have the following process. Let me draw it in color. You can have the process where a color red quark, a color green quark, a color red, and a color blue can come all together and disappear. Okay, and that is allowed. So the only way that redness, greenness, and blueness can disappear out of the theory is if they come into one and the same point and they disappear at the same time. Okay, so this is how SU3 acts. SU2 is similar, if you have a down quark, the black line represents a down quark. Okay, so focus on the second graph. You have a down quark coming, and a black or a down quark wants to convert into an up quark, which I have drawn purple. The only way that a down can go into an up is by emitting a particle which is called a weak gauge boson, or a W in this case, which has 1 unit of downness moving along and 1 unit of purpleness coming back. See, the key point in all of these processes is that if you draw a little box, let me draw a little black box around this is called the vertex, the interaction. There is 1 unit of redness coming in and 1 unit of redness coming out. 1 unit of greenness coming in and 1 unit of greenness coming out. So in all of these cases, the net amount of redness and greenness is maintained, is conserved. And the same there with blue and purple. Blue line comes in and out, purple line comes down and out again, in and out. And so this is called, and again, there is only one exception. If you have an up and a down together in a specific combination, can disappear. Sometimes you can have an up and a down quark come together and disappear. And this is an attribute. Actually, it's due to the letter S in this group, SU2. Electromagnetism works very similar to the U1 is essentially electromagnetism. So the way it couples is an electron emits a photon and continues to be an electron again. Notice I've written G1 and G2 there. G1 is the coupling of the U1, which means the strength or the square root of the probability with which the first process happens is G1. For the second process is G2. It's called the coupling constant or the coupling strength. And this, of course, is called G3. Okay, so 3 coupling constants that characterize strong, weak, and electromagnetic interaction. Let me see. Now, okay, let me see if I had. Yeah, this is, so these gauge forces play a crucial role in the theory, in particular the gluons that you see here, the gluons that you see here are responsible for the strong interactions. They're responsible for what keeps the quarks inside and up or down. Yeah. Oh, okay, thank you. Until when do I go?
9.
Oh, okay. 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 Now here I have what I've told you so far is that I have introduced the Higgs particle, these 4 particles, the gluon, the photon, the W boson, and I forgot to mention the Z. The Z is also a boson that is associated with the weak interactions with this SU2. Okay. And the first family of particles, which are called up, down, electron, and neutrino. Here I have written down the second generation of particles and the third generation. Okay, so the second generation up quark is called charm, the down quark is called strange, and the third generation it's the top and the bottom. And the corresponding leptons are the muon and the tau, nu muon, tau neutrino. So these are the 3 generations of particles. They have identical interactions as far as SU3, SU2, and U1. All of these, under all these symmetry groups, they have exactly the same repetition of this pattern, triplets, doublets, etc. The big difference is the way they interact with the Higgs particle, which gives them very different mass. For example, the up quark has a mass which is about of order of 1 MeV, which is 1,000th of the mass of the proton. And the top quark has 173 GeV, which is 173 times the mass of the proton. So the hierarchy between the up and the top quark is about 5 orders of magnitude. And the charm is somewhere in the middle. And similarly with this, so you have from the electron mass to the top, which is the lightest of the, except for neutrinos, the lightest of the fermions, to the top quark, there is a hierarchy of about 100,000 in mass. The neutrinos are approximately massless, and that is reasonably well, this is really understood, and I'm not going to have time to discuss it. But one of the challenges that, possible challenges to face is how to account for all this variety of elementary particles and properties, okay? The variety of masses in particular, which is very perplexing. Now I want to move to one of the reasons, one of the fundamental reasons for going beyond the standard model, which is the so-called hierarchy problem, okay? And to illustrate this, let me, actually, I need to change, okay. So now I have presented to you the forces and the families of the standard model. So now I will begin telling you about reasons for going beyond the standard model. The standard model has, as we said in the beginning, too many particles and too many, in a sense, even too many forces. There is strong, weak electromagnetic interactions and gravity. And too many numbers, too many parameters associated with it. And let me begin here. And this seems to be going contrary to our ideas for minimalism in science. So the idea of minimalism started, I forget, with Occam, who was a priest. I think he was, I forget, 1300s. And he postulated that entities must not be multiplied beyond necessity. And there was actually a competing principle, which Leibniz was advocating, which is the principle of opulence, which stated essentially the opposite, that all possibilities should be realized and the world is a much richer place. But Occam's razor has served us very well in science. That's a foundational reason for why there is some simplicity, economy, and elegance in science. And this is, oops, this I showed already. You'll have to go through it. I have no option. Okay. And how is Occam's razor implemented? Well, one of the ideas for implementing Occam's razor is through the idea of unification. Okay, so unification is an attempt. Unification means taking things that look apparently different and reduce them to one and the same. So the idea of symmetry is very much in that spirit. You know, in principle, each orientation of the sphere is like a different object, but because all orientations look the same, you can think of it as one. The first example in modern science of unification is, of course, Newton, who unified terrestrial gravity and celestial gravity. This was a major, major breakthrough in scientific thinking for many reasons. First, because it was unification. The same equations that describe how an apple falls also describe how the moon moves around the Earth. The other reason is simply philosophical. During that time, which was 1600s, many people believed that the celestial and the terrestrial belonged to a different domain, and that we humans couldn't really understand celestial phenomena. Celestial phenomena. And Newton showed that by doing experiments and by just thinking on our planet Earth, we can discover truths that are valid in faraway places, anywhere in the universe. The laws of nature that we discover on Earth are no different than in Andromeda or any other place. So this was an extremely big step in modern science. And this story of unification repeated with Maxwell, who showed that electricity, magnetism, and light are unified into one theory, electromagnetism. He predicted electromagnetic waves, which was discovered about 20 years after his death. And this story again repeated in the 60s with the weak force and the electromagnetic force becoming unified into the so-called electroweak force. So this is a pattern that has been happening in science over and over and again. And now the challenge is, now we are still left with well, you can call it three forces, I guess. But even though it's really four groups, it's U1, SU2, SU3, and the gravitational group. So, so how do we unify all this? Now, next time I will introduce the so-called grand unified theories, which tell you how you can unify electroweak force and strong force, and it has some very important experimental, and a very nice piece of experimental evidence. I'll introduce this when we talk about supersymmetry because it's more appropriate for that. But the question is, how do we also bring gravity in the picture? And why is this so hard? Well, it's so hard for the reason I was advocating before, which is that gravity seems to be far weaker in magnitude than all the other forces of nature. So if you take a proton and an electron, their electric force is 40 orders of magnitude stronger than their gravitational force. Okay? So how can it be? How can you possibly hope to unify gravity with electricity when they are qualitatively so very different from each other? And this is the essence of the hierarchy problem. And I want to give you a way to understand this. Now, I'm slowly entering the field of physics beyond the standard model. I want to discuss theories with large extra dimensions to explain to you how they account for the weakness of gravity. And for this, let's imagine the following. Imagine that this two-dimensional piece of paper that I have represents our three-dimensional space. Okay, so you have to imagine it as being infinite, well, very, very large piece of paper. Even though it's two-dimensional, think of it as being our three-dimensional space. And imagine, as it is easy to imagine now, that it's embedded in an extra-dimensional space. So the dimensions of the piece of paper are width and depth, but there is an extra dimension, which is called the height, which is perpendicular to this piece of paper. Okay? And so similarly here, I've depicted exactly this here. So here is the piece of paper. It's embedded in one extra dimension in this picture. Okay? Now, and imagine that our universe is floating inside an extra dimensional space. In this case, I drew just one extra dimension. Now, all the things we are familiar with, here is atoms, magnetism, electricity, light, think of them, all of these, as living strictly inside the three-dimensional universe. In other words, they don't extend into the extra dimensions. Okay? Except for gravity. Postulate that gravity is the only entity, the only force, if you wish, that spreads into the space of the extra dimension. Then, according to the proposal of extra dimensions, that can account for the weakness of gravity. And the way it can account is that because gravity spreads or propagates inside the space of extra dimensions, it dilutes its strength. Whereas electricity and magnetism and all the other forces don't lose their strength because they stay in our three-dimensional universe. So if there are extra dimensions inside which gravity can dilute its strength, but the other forces don't, this is a nice and geometric way to understand why gravity is so weak. Now you can ask, if you have just one extra dimension, how big does it have to be? Does it have to be to dilute gravity adequately? And it turns out to be astronomically big. It would be excluded by, it would be on the order of the size of the solar system. So clearly this would be excluded. We know that space doesn't act as a five-dimensional, gravity doesn't act like, and it has an extra dimension. Or else, for example, Newton's law would be like 1 over r cubed. The force law would be 1 over r cubed instead of 1 over r squared if there was an extra dimension. So, however, if there are two extra dimensions, then even if they are as small as 30 microns, that can account for the weakness of gravity. And if there are three extra dimensions, the extra dimensions can be even smaller. So this idea suggests that we should look for extra dimensions using, for example, gravitational experiments, because this is the only force that propagates inside the extra dimensions. And as I will explain in a short while, such experiments have been done, but already the Large Hadron Collider is looking actively into the possibility of extra dimensions. And to appreciate how they look for it, consider the following analogy. It's very similar. Replace our three-dimensional universe with the surface of this pool table. So this represents the three-dimensional universe. The billiard balls represent elementary particles, and the collisions of billiard balls, collisions of elementary particles, for example, at the Large Hadron Collider. Okay? Now, normally when billiard balls collide, they still stay inside their two-dimensional space. The analog statement is when protons collide at the Large Hadron Collider, they stay in our three-dimensional space. They don't jump out into the extra dimension. However, there is one thing that does propagate inside the extra dimension. In the case of the pool table, it's sound waves. Okay? So even though the collision happens on the two-dimensional surface of the pool table, the sound waves comes out in all three dimensions. This means, and this is the analogon of gravity. Okay? Gravity propagates inside the extra dimension just like sound waves propagate here. So this, now, imagine now a collision of two billiard balls. If you collide two billiard balls and you compute, you measure their energy just before the collision and just after the collision, then you can infer about the existence of sound waves by trying to look for a deficit in the energy before and after the collision. This is simply because sound waves carry a certain amount of energy which is taken away from the billiard ball system. So even if you cannot hear at all, when you collide when you collide two billiard balls, by measuring their speeds very precisely before and after the collision, you can infer that there is some missing energy, and you can infer the existence of sound waves. Okay? Same thing, LHC is trying to do exactly the same thing for gravity. They are colliding protons, and they look for something that's called missing energy signature. Okay? And the idea is that if there are gravitons, when protons collide, if there are gravitons produced, they can manifest themselves with missing energy. Furthermore, the characteristics of this missing energy are fairly well, they are very well determined from the theory. By looking at the characteristics at the spectrum of missing energy, you can infer even that it's due to extra dimensions, how many extra dimensions there may be, etc. So this is this is one of the several things that the Large Hadron Collider is looking at. It's by no means the only thing. The main focus of the Large Hadron Collider is a theory called supersymmetry that I don't have time to discuss today, but I will discuss in a couple of weeks. In the remaining few minutes, I want to, I want to keep the material a bit more entertaining and demanding less concentration. So I'll tell you a few things about the Large Hadron Collider that I actually will need next time. So I'm sure you've all seen this picture. This is the ring of the Large Hadron Collider. The Large Hadron Collider is a machine that is built in Geneva, Switzerland. It's about 100 meters underground, and it's a 27-kilometer circle. It accelerates protons. Half the protons go clockwise, the other half anti-clockwise. And the protons go thousands of times around every second. And they collide in 4 specific spots that are called the detectors: CMS, LHCb, Atlas, and Alice. And physics beyond the standard model is mostly investigated in CMS and Atlas, and a bit in LHCb. And Alice is mostly for heavy ion collisions. So that is the machine that is now running and is testing these theories that we started talking about. Here gives you a concept of size. This is 100 meters underground for radiation purposes. And this is the CMS detector. The Atlas detectors is far bigger. This is really the small brother. I should have. So this is just for scale. This is the person. So it's a few floors high, and it's fully all of these things. These things are, of course, detectors. They detect various particles: electrons, muons, photons, hadrons, and different parts of the detector that have different particles. And the collision regions, you take data, you look at these collision regions, take data. The data are channeled by miles upon miles long of cables to several computers, and they're being analyzed. And in fact, the analysis is amazing because the rate of events is huge. So you have to immediately, when a collision happens, decide whether you are going to write it down on tape, namely to keep record of that, the characteristics of that collision, or just ignore it. And you have to do it efficiently because otherwise there is a billion of data per second. It's unmanageable. So there are the so-called, there are several cuts that you have to do to the data. So there is, it's a huge operation, many thousand scientists. And this is amusing. The total amount of energy, so there is protons circulating that if you take the total energy of the protons, that are at any one instant at the LHC when it's running, then you find that first the cross section is smaller than a human hair, of order 10 microns or so, and carries the energy of one TGV train. TGV means très grande vitesse, or very fast, the bullet train that runs through Europe with 200 kilometers per hour. So as I was saying, there is 1 billion of collisions, so you don't write them all down. You have to have a rapid criterion of what is interesting and what's not interesting. One thing that qualifies for interesting is what I mentioned before, namely energy loss. If you see an imbalance in the initial energy of the collision versus the final energy after the collision, then that's an indication that you should take a look. Other indications are the following. If you produce a heavy particle, a heavy new particle that you've never seen before, which will be the case because the energies are, these energies are much higher than the masses of all particles. So if you produce a very heavy particle, it will be produced at rest. And it will decay in all directions isotropical. In particular, if the beam is horizontal, it will decay a lot in the vertical direction. So you look for what's called perpendicular momentum events to be differentiated from the forward events. When two things collide and they produce light stuff, the light stuff tends to go forward. So there are all kinds of cuts. As I said before, the machine turned on March 30th of 2010 at 7 TeV, which is 7,000 times the mass of the proton, and now it's running at 13 TeV, 13,000 times the mass of the proton. And desire. Okay, and here I have drawn what I was talking about before, that the analogy between the billiard ball and the LHC machine is that instead of colliding billiard balls, you collide protons now, and gravitons can come out of the space of the extra dimensions and manifest themselves as something missing, some energy missing from the system. I should say in these theories there is another ingredient that I don't have time to discuss. There is also some other particles which is called a vibrating string. The theories I'm talking about turn out to be string theories not far from the electroweak scale. So there are other signatures of these frameworks that we will not discuss today. This is very interesting. Occasionally in these theories you can produce a micro black hole. You can collide two protons and produce a micro black hole. And this created a big fuss in the press. There was lawsuits trying to get CERN not to get started. This is not a concern for many reasons. First of all, these black holes are very small. They are, their mass will be at least a few TeV, which means they are absolutely tiny, 1/10,000th of the proton mass size, and they decay instantaneously way before they have a chance, to travel from one atom to the next. Okay? The fear was that if a black hole forms and starts eating, then it will grow and it will not evaporate, and as it grows, it will eventually consume Geneva and the whole world. So I don't have time to show you. Maybe I thought I had it in one version. There is a nice movie that dramatizes this occurrence. How a black hole will manifest itself? Black hole is a fairly democratic entity. It is characterized by temperature, so it democratically will emit all the particles it can at that temperature, and you will have a many particle final state with all kinds of particles sprayed in all directions, 40 final states, etc. So they are looking for this. I mean, They get sometimes these events, but obviously the statistics is not big enough to confirm anything. These theories remain very speculative. Now, the theory of the theory of extra dimensions has many ramifications that I want to get into now. So if this is our universe, this is our three-dimensional universe on the surface of this piece of paper, floating inside the space of extra dimensions. What about other so-called parallel universes? Couldn't you have other three-dimensional spaces that are floating inside the same extra-dimensional space, and on which there are, different people, maybe not even people, maybe the laws of nature are different in this parallel universe than in our universe. All of these are possible. In fact, if there is extra real estate in the extra-dimensional space, it's hard to imagine that there wouldn't be other parallel universes, especially if there is, 1, 2, 3, 4, 5, or 6 extra dimensions, all of which could be possible. There will be, in general, several different three-dimensional spaces that you can embed in it. All of these three-dimensional spaces can be possible universes. So the new worldview is that we are most likely not to be alone. If there is an extra dimension, there is likely to be one parallel universe and most likely several parallel universes. I represent them here with different color code to signify that they may have different laws of nature. Okay, so this one may be ours, and this one, so the electron mass, for example, can be different here and there, which will make a huge difference for chemistry, biology, life, etc. Or so it could be that all of these universes have different physical laws, and that is the beginning of that leads to the so-called multiverse. That if you have extra dimensions, the one way to realize a multiverse, that's not the only way, is that you have extra dimensions of space, and inside these extra dimensions there float many three-dimensional spaces that are our universe. In fact, they don't even have to be three-dimensional. There could be four-dimensional and two-dimensional universes. Now, they wouldn't be much like us, but they could all exist. In the fundamental theory, the so-called string theory, where these entities appear, there is 10 or 11 dimensions. So there is a lot of space to put things in. So you can put multidimensional spaces. So this is a sort of ultimate demotion. We've been going from demotion to demotion throughout our history. First, we thought we were at the center of the universe. Then we became, oh, well, we're not, the sun is the center, and we are sort of near it. So it was okay. But then we found out our solar system is just one out of 10 billion in our galaxy. Then our galaxy is not special because there is no special point in the universe. They are all the same. So it's just one out of 100 million other galaxies. Now we seem to be led in this, that even our universe is not particularly special. It's one of many. Our laws of nature, it's a purely environmental study. We just happen to be here, so we discover the laws we discover because we happen to live here. If we could travel to other universes by traveling through this extra-dimensional space, we would encounter different physical laws. We is a generic we, because I don't think we would survive the change of these physical laws, but you get the idea. So the idea of minimalism that I started advocating, that led naturally to unification, to the idea of unification through Newton and Maxwell and electroweak model, is now competing with Leibniz's idea of plenitude. Okay? So here is how Leibniz said it. The best of all possible worlds will contain all possibilities, with our finite experience of eternity giving no reason to dispute nature's perfection. So his idea of perfection was anything goes, and essentially the opposite of And you can tell from their hairstyle the difference in their philosophies. And so, and we are encountering a similar situation where, you know, the laws of nature, where there may be other universes where the laws of nature are different even. So how do we look for other universes? And that, if this is science and it's not just, you know, conversation, we have to find experiments that can test this idea. And people have been thinking a lot, mostly at Stanford and in several other places now, for possible tests of this idea of what's called the multiverse. And let me see. Okay, so people have very violent reactions to the idea of the multiverse because it's the last time. We don't want to be demoted again. And so this principle of minimalism that has been driving us was also driving people in the 1600s. Most people in 1600s believed that there is just one solar system. If you don't recognize, by the way, this is one solar system. If I cannot see from here, presumably the Earth is at the center, of course. And so I'm not even, yeah. So for the solar system, they believed that there is only one and we are very special. And the fact that we find, now, if there is just 9 planets, it's just a miracle that there is one of them that supports us, that is just right for us to exist. You know, if you think of the number of coincidences that it takes to have life on Earth, it's mind-boggling. First, there is the distance. It can't be too close, or it will be too hot. Too far, it will be too cold. But that's the simple. Then you have all the chemistry, all the elements that are important for the evolution of the Earth and for the evolution of life on the Earth have to be sort of put together by divine intervention, because if you have only 9 samples, it's very unlikely that we would form in one of them. So now, the principle of plenitude, on the other hand, this is one instance where the principle of plenitude really worked better than the principle of minimalism, because as we know, there is many solar systems. There is 10 to the 22 or 23 solar systems. There is 10 to the 11 galaxies, and galaxies 10 to the 11 stars. So there is an amazing variety. So what used to be a sort of divine intervention to account for our existence in the one and only solar system is now just a statistical oddity. There's probably many places where the conditions are right for different forms of life to form. In addition, by the way, I should say, this has an amazing impact on what we consider reasonable questions. For example, if there is only one solar system, then what are the deepest questions to ask? Well, you have to ask the distance between the planets, or let's say the distance of the planets from the sun. That sounds like very fundamental quantity, and people try to embed it into sizes of platonic solids that are one embedded inside the other, and they got things right to 10%, which is not so bad. And so the fundamental quantities of the universe were the distances of the planets from the sun. Now, of course, we consider that's a historical fluke. It is an accident, you know, things flying in the solar system. Some historic accidents led to so it was demoted. This question was demoted from being the deepest question in physics to being just, history. So similarly today, perhaps not, we think that the laws of nature are extremely important. This is the deepest question to ask. What is the electron mass? You know, why are the gauge couplings? Why there are these groups? Why there is this, you see a tremendous amount of complexity, these groups and these particles, and why is the world put together the way it is? Well, maybe it's deep. Maybe if there is a multiverse, it's not deep. It's one of many possibilities, and it is the place where the laws of nature suit us. For us, by us I mean strictly us, with our chemistry and biology, for us to form. So whether there is a multiverse or not has a huge impact on the philosophy of science, on what we consider good questions and what we consider historical or environmental accidents. So this is, let me see. Now, I should say on this that there was this point of view of minimalism versus plenitude, which is one of the hottest debates of our time. And several people at Stanford, including Lenny Susskind and Andre Linde, sort of pioneered this multiverse point of view, and believe that that may be the way the world is. And in analogy to these people, back in the 1600s, there was a person called Giordano Bruno, who also advocated the existence of many solar systems. He said something very fancy in Latin about multiple worlds and life forming. And of course, he paid for it by being fired, literally being put in 1600. And in fact, his burning was one of the reasons why Galileo sort of took it easy with the Pope in the, I guess it was 1630s. So this is not quite the way it feels, but I tell my junior faculty not to work on the multiverse. And unless you have tenure, don't do it. So to be continued. Okay.
For more, please visit us at stanford.edu.